Satellites around our planet provide communication and internet and connect our world. But collisions are an increasing problem, especially in low Earth orbit. Thermospheric drag, which is the braking force exerted on satellites as they orbit the Earth, is a major factor in predicting where spacecraft are and when collisions might happen. Thermospheric drag is highly influenced by the sun, specifically solar irradiance, and the drivers of geomagnetic storms. Understanding and better modeling these relationships gives mission managers improved estimates on numerous aspects of spacecraft management. The Thermospheric Density Continuous Learning Team has expanded Karman, a data-driven AI pipeline, which can significantly outperform state-of-the-art models used in satellite operations. The goals are twofold: to build a continuous learning system through live ingestion of solar drivers and satellite data, and to better enable forecasting, updating Karman's abilities in an ever-changing and more congested space environment.
Hello everyone, and welcome to the presentation of the Thermospheric Density Continuous Learning Project. This FDL-X Heliolab project has been developed by our team of researchers and faculty members, myself, Jordi, Aishwarya, Will, Sankalp, Giacomo, and James, with a variety of expertise in the domains of space weather and machine learning, including data science, astrodynamics, and computer science. The challenge revolves around the life of satellites in the low Earth orbit, responsible for providing communication and navigation solutions while subject to the effects of the thermosphere and solar activity in a very congested environment. Thermospheric drag is one of the driving forces acting on satellites in the low Earth orbit, and it has an enormous impact on their trajectories, as you can see the demise of these satellites shown here, and therefore is crucial for collision avoidance. The main driver of satellite drag is thermospheric density, which in turn brings the major source of uncertainty in its prediction due to the influence of different space weather phenomena. These physical phenomena are directly caused by the interactions between the Sun and the Earth. Different processes associated with solar activity interact with the Earth's upper atmosphere and with the Earth's magnetic field, influencing the ionosphere and thermosphere. The effects of some of these different processes on the upper atmosphere can be observed in this animation. At first, we see the different layers of the lower atmosphere. When we zoom out, we can see the thermosphere, which expands and contracts according to the day-night solar cycle. But we can also see all these fluctuations near the poles, which are caused by a strong geomagnetic storm and its interaction with the Earth's magnetic field, showing the complexity and variety of events affecting the thermosphere. In this context, the goal of this project has consisted of developing a data-driven solution that provides thermospheric density predictions that enhance the safety of space missions and improve the operational success. All that by leveraging data from satellite missions as it becomes available. Therefore, turning the challenge of dealing with this congested upper atmosphere into an opportunity for devising improved thermospheric models. And to understand how we're going to do that, let's take a step back and see how this is done in the lower atmosphere. Weather balloons play a crucial role in obtaining distributed measurements that are then used to make accurate weather predictions. However, we don't have weather balloons that can get to space. Or do we? Weather balloons in our case are none other than satellites, which were not originally designed to measure thermospheric density, but that now they can provide us with these measurements alongside with their original mission. In particular, by means of such density measurements, satellites are able to inform our models in order to improve our upper atmospheric predictions. This task has been accomplished throughout the years by means of Karman, a data-driven model for the estimation of thermospheric density. Karman has shown enormous success, outperforming state-of-the-art thermospheric models. In this year's effort, we have expanded Karman's horizon, developing a continual learning approach that permits, first, the live ingestion of data from satellites and different physical drivers, and second, a continuous update of the model, enabling improved density forecasts. Now, I will hand it over to Will, who will put this work in the context of machine learning technology readiness levels.
Thank you, Jordi. Previous iterations of Karman sit at level 3 and 4 of development. through our efforts this year, we have transformed Carmen into Carmen Continual Learning, or Carmen CL for short. And in the next few slides, I'll show you how we did this. In order to reach this higher level of development, we've had to build an autonomous data ingestion and continual machine learning pipeline using Google Cloud Platform. It is this pipeline that gives life to the continual learning and live density forecasting capability of Carmen CL. As you can see, this is a little complex, so in the next slides, I will break this down. The first component in advancing Carmen to higher technical readiness levels is the design of a live ingestion data pipeline. This pipeline automatically pulls data from 11 different satellites as soon as that data becomes available and provides us with an ML-ready data input that is key to forecasting thermospheric density. But what are these inputs? They are satellite data, including our target densities and the corresponding time and positions, the solar and geomagnetic indices, solar wind parameters from Omni, solar irradiance measurements from SOHO, and model-derived density from MSIS. In addition to this, the pipeline is created using some software called Terraform. This software allows us to effectively template sections of the pipeline, which allows us to quickly and easily add new parts should new satellites or other sources of data come online. The data ingestion pipeline is now running live. So what happens when we acquire new data and want an updated forecast? The first thing that happens is we check the new data against existing distributions. And this is what you can see depicted in the two plots here. If the data is consistent, as shown in the green box, then we follow this arrow and use our existing Carmen model to give us the density forecast. But what happens if the data distribution is different, as shown in the red box? This automatically re-triggers our training of our ML models. And we don't just have one of these, but an entire zoo of different algorithms. Once trained, we compare their performance against each other and select whichever is best and use that to get the density forecast. This newly trained model then becomes the new default for the next set of data that is acquired by the pipeline. And now I'll hand over to Aish, who will talk about the results.
As Will mentioned, we would like to demonstrate what Carmen CL can do. And here we are showing you exactly that. This is a global map of the forecasted densities at the top of every hour for 3rd February 2022. I'd like to highlight two things here. These forecasts are for a day of a month, which is completely unseen during training or validation. And two, we have a forecasting lead time of 100 minutes. So we are predicting 100 minutes before an event occurs. We also see that the model captures the bulge in thermospheric density, which follows the sun, giving us confidence in our overall predictions. As you saw earlier, our pipeline is flexible and supports many different inputs. This allows us to run different experiments, like checking input importance and the effects of changing lag and resolution. Let's look at how input importance affects performance. In this table here, the green and red traffic lights show you the inputs that have been included or excluded in some of these experiments. We're highlighting a few cases here, and essentially, the lower the MAPE metric that you see on the right side column, the better the performance. If we focus on the bottom row, we see that the more the data, the better the performance. However, if you look at the second to last row, we see that just including two inputs, SOHO and Omni, gives us nearly similar performance. Now we can also run experiments by changing the length of the time windows. And what you're seeing here on the left is the change in performance for different time windows. Green is the best performing time window and red is the difference relative to this. And we see that as time window increases, performance degrades. Similar to time windows, we can also experiment with the history lengths. And here we see that this has less of a drastic effect on the MAPE metric, but in general, longer history results in better performance. Now, I'm going to pivot for a moment to talk about a major solar event that happened this year. To give some context, the sun goes through a 11-year solar cycle, and we are currently in solar cycle 25, and we are in fact at the peak of this cycle. In May of this year, there was an X class flare, and maybe some of you remember the effect of this, which was auroras that lit up our skies. However, it also kept spacecraft operators on edge, as you can see from this news headline. So the question we asked was, can Carmen CL foresee this event? And let's look at the answer. So indeed it does. If you look closely at this animation, the little red dots are forecasted densities for this May event with a lead time of 100 minutes. And the shaded orange region preceding the forecast is the historical information we've used to obtain this forecast. And you see that it does predict the sharp increase in density. Now, at the very end, we overlay the model predicted densities from EMSIS for comparison, and we see that the EMSIS results are not only worse, but they couldn't have been obtained in advance because it does not have predictive capability, whereas Carmen can provide 100 minutes of lead time. Overall, we are able to forecast and anticipate change in density, and as a result, we could potentially provide adequate warning to satellite operators of an incoming event like this one. To summarize, we've developed a new thermospheric density model that can meet space operation demands, and it also outperforms empirical models in accuracy. We've extended Carmen for forecasting and implemented a continual learning framework with live data ingestion, continuous model updates, and real time inference. So, what does this mean in the bigger picture? With this tool, we will be able to possibly avoid thousands of spacecrafts maneuvering at the same time when we are hit by a geomagnetic storm and avoid consequences like collisions or unsafe re entry of satellites. To wrap, I would like to thank the FDL-X Heliolab team, our public and private partners, and all the reviewers who have provided us with invaluable feedback.